Hello kids, welcome. Let's discuss today's JEE Mains question paper, what we have. Now child, you must be aware that for this particular test, the chapters which were of 11th as well as 12th of organic section. Yeah, the first chapter I think so what you must be knowing is general organic chemistry, second is nothing but hydrocarbon, third one is nothing but isomerism, fourth one is nothing but POC, was of 11th standard. From 12th standard child we had got first chapter which is halogen containing compound, that is halogen derivative, alcohol, phenol, ethers, aldehyde, ketone, carboxylic acid, amines, biomolecule, and I hope this is clear to you all. Let us see the first question what you have got on the screen. Now the first question says that in a given compound below what you can see, which nitrogen is protonated first when treated with HCl. Now basically bacha, if you know HCl is an acid, obviously as per the situation over here we are talking about that it will react with the base. Now the question asked is, what is a base? Base is nothing but a proton acceptor or electron pair donor. Now over here I think so child, you have got two nitrogen, nitrogen 1 and nitrogen 2 which has been labeled. Is it clear child? Now out of these two nitrogen, the question is which one is going to get protonated? That's the question. Now child, if you remember one important point when we had discussed resonance, the doubly bonded nitrogen lone pair will not get involved in resonance, will not get involved in resonance, whereas the other nitrogen what you can see can get involved in resonance. Now the question is how it is related to basicity. Now the answer is very simple. Your basicity, your discussion of basicity is inversely proportional to lone pair electron involved in resonance. That means in a simple terms, the lone pair one which is involved in resonance will be less basic and the one which will be not involved in resonance will be more basic. So over here if you see nitrogen 1 lone pair is not involved in resonance, so that will be more basic, whereas the other one would be a less basic. So who is going to get protonated first? Obviously your nitrogen 1. So as per the correct option, your N is 1, first nitrogen or nitrogen 1 is going to get protonated first because its lone pair is not involved in aromaticity. That means your correct answer for this question is C. I hope this is clear child. Let's proceed to the next question what we have. Now here child, what is given? What is the IUPAC name of the following compound? Now before we start anything, I think so if you check over here, the number of carbon atoms are 1, 2, 3, 4, 5, 6, 7 and 8. That means there are 8 carbon atoms with 3 double bonds. So I think so if you check the name, everywhere I think so the name is same. Yeah. So there is no issue in the naming system. The discussion is about what is E and what is Z. I think so child, we all know in case of geometrical isomers, we have got one type of a nomenclature what is used as cis and trans, but there is another nomenclature also which is used which is called as ENZ nomenclature. Now whenever if you have got an alkene shown like this and whenever if you have got an alkene shown like this, if you check properly, over here you have got one hydrogen on this side, one hydrogen on this side. Here again we know that one of the bond will be up over here and the another one will be down over here. So if you check over here, as per your EZ nomenclature, we have got one rule what we call it as CIP rules. According to CIP rule, the one with the higher atomic number will get higher priority and over here one with the lower atomic number gets lower priority. So over here your H will get number 2, your H will get number 2. This group will get number 1, this group will get number 1. That means where you have got both the higher priority groups on same side, we call it as Z isomer. Whereas in this case child, if you see hydrogen is second, this group is 1, again this is 1 and this is 2. So both the higher priority groups are on the opposite side, we call it as an E isomer. So basically as per the discussion, it's very clear and very simple that over here your both the hydrogens are on the same side if you check. So this has to be a Z isomer. Over here if you check, one bond is up, so this hydrogen is over here for the second double bond, and here the hydrogen, I think so both of them are opposites, it's an E isomer. Again in the last, the right hand side double bond, what is left out, you have got one bond up, so H is over here, and in this side also H is over here. Again both the H's are on the same side, means again it's a Z isomer. That means the configuration what you have got for this double bonds are Z, E and Z. I think so you can see the most appropriate answer what you can see is Z, E and Z. So it's a 2Z, 4E, 6Z, octa 246 triene is a complete IUPAC name of the given compound. I hope this is clear, child. Let's take the next question, bacha. Now, which of the following resonance structure would contribute most to the resonance hybrid of the molecule? Now, before we start with the discussion, I think so this discussion is based on your major minor contributors, correct? Now, when you talk about major minor contributor, child, the first rule if you remember was maximum atom completing its octet. Yeah. The second situation was maximum number of pi bond. Now, see over here, if you see there are only one pi bond you have got. Over here also there is one pi bond. In this case, we have got two pi bonds. Here also we have got two pi bonds. That means one thing is very clear that this has to be less stable. This has to be less stable. That means these two has to be more stable. Now, out of these two, if you remember, we had got one point, and that is what? Your neutral resonating structures are more stable, but at the same time there is one problem. Nitrogen over here, if you see, yes, is given in a form of as a tetravalent species, since it is not that stable because it has been not given as charge also over here. But whereas here you can see it's a properly given, oxygen getting a negative charge, nitrogen getting a positive charge. So out of these two options, the most appropriate option is C. Your D option cannot be the answer. I hope this is clear, child. Is it clear? Let's take the next situation, bacha, what we have on the screen. Yeah. Now, the next question what we have is, now the question is, what is the order of enthalpy of hydrogenation of the following compound? Now, the question is, child, if you remember heat of hydrogenation, we have done somewhere in past that your heat of hydrogenation is inversely proportional to stability of alkene. Is the term clear? Now, child, before we start, one thing, heat of hydrogenation, let's discuss the stability. Now, out of 4 examples, if you see the first example, it's very simple to understand. It's a resonance stabilized alkene, whereas in none of the cases resonance is involved. So, I think so out of all, which one is more stable? The first one is more stable. If this is more stable, that means its heat of hydrogenation value would be minimum, and I think so one has to be a minimum. Now, out of this 3 example, you can see one is not a minimum in this case. Even in this case also one is not minimum. Yeah, in this case your 1 is minimum. Again in this case your 1 is not minimum. That means your correct answer for this is C. I hope this is clear, child. Let's take the next question. Now, this is one of the discussion we have done in the lecture. Para-nitrophenol and ortho-nitrophenol are separated by. Now, child, you should know one thing very clearly in this. Your para-nitrophenol, yes, shows intermolecular H bonding, yes, and whereas in case of ortho nitro, it shows intramolecular H bonding. Now the question is what? The question is, how will you separate these two which are in mixture? Now, you should know bacha, in a steam distillation child, you can only use this technique if one of the compound is steam volatile in the mixture, and here you can see your orthonitrophenol is a steam volatile compound, whereas paranitrophenol is non-steam volatile. So, here you can easily separate them by using steam distillation as a technique. I hope this is clear. We have discussed also in the lecture, bacha. Yeah, let us proceed with the next question. Now, here the question given to you is how, one butane can be distinguished from 2 butane by using which reagent? Now, basically when you write but1ine, yeah, but1 butane, the structure is something like this, yeah, and here you have got H, here you have got CH, here you have CH2, correct. Now, the other compound is nothing but but2ine. Now, but2ine is something called as like this, where you have got CH3 over here and CH3. Now, before we start anything, let us first try to analyze what is the basic difference between both of them. I think so, this is called as terminal alkyne, or the most important term, can I call it as an acidic alkynes? Yes, all terminal alkynes are acidic alkynes, correct? And whereas in this case, it is a non-terminal alkynes or non-acidic alkyne. Now, the question is, child, how will you identify acidic and non-acidic alkyne? So, there are two tests, bacha, what we have. One, I think so, if you remember, is ammonical silver nitrate, and the second test, if you want, you can use it as ammonical cuprous chloride. And in both of them, child, if you remember, when you are using ammonical silver nitrate, you get white PPT, and in case of cuprous chloride, you get red PPT. So, both these tests can be used to as a laboratory test to identify terminal alkyne and non-terminal, or acidic and non-acidic alkynes. I think so, in this case, child, your but1ine is acidic and but2ine is non-acidic. So, that can be very easily identified by using ammonical solution of silver, that is nothing but Tollens reagent. Yes, ammonical silver nitrate is also called as Tollens reagent. Yes, is it clear, child? Let us proceed with the next question. Now, here, child, this is one of the reaction given to you. Okay. Now, basically, if you see over here, I have got an alkene, and here I have got an, now see, one oxygen is extra in this, child, bacha. So, this is not an acid, it is peroxy acids, and peroxy acids are used for oxidation. They are used for oxidation. And now, when alkene gets oxidized, will I get nothing but epoxide forms? Yes, so here your oxygen will get added to both the carbon atoms, and you will get a 3-membered ring, epoxide rings. And I think so, we have done in a lecture also that which are the examples of per acids. I think so, we have done peroxyacetic acid. We have even done peroxy trifluoroacetic acid. Yes. So, the answer in this case is very simple, child. The answer is A, where epoxides are formed. I hope this is clear, child. Let us take the next question, bacha, what we have. Now, here, child, which set of reagent in correct order would be accomplished the following transformation? Now, bacha, before we start anything, let us first try to analyze what they have given. Now, see over here, they have given 1 pentyne and cis-2-hexene. First of all, you should know there are 5 carbon atoms, and over here there is 6 carbon atom. That means the first change what you should remember is number of carbon atom is changing. And point number 2, your triple bond is getting converted to double bond. Your triple bond is getting converted to double bond, and in that also your product has to be cis. Now, before we do all these things, there are certain logic, if you remember, child. See, you have studied in somewhere past discussion that alkynes can be converted to an alkenes, where cis and trans both alkenes can be obtained, one by Lindlar's catalyst and one by Birch reduction. In case of Lindlar's catalyst, you will get cis alkene, and in case of Birch reduction, you will get an trans alkene. Do you remember this, child? Now only that is not a problem. Even here the number of carbonyl has to be increased. So what has to be done? Now you know there was one reaction, child, where lower alkyne gets converted to higher alkyne. So what was that reaction? Yes, let's try to recollect. Now what is pent 1-ine? Suppose if I write pent 1-ine, so is it nothing but you have got pent 1-ine. Is the term clear? I think so. This is the first carbon atom, what you can see over here. Now when this is treated with sodamide, I think so we all know that a sodamide, pent 1-ine is an acidic in nature. Yes. So what will happen in this case? You will have first a salt formation taking place over here. So you will have got over here your triple bond, but here it will be your H has lost conjugate base, and you will have got Na part over here. This is nothing but a salt. Now if you want, I can put a carbon over here. Now what will happen? This has to be treated with methyl iodide. Now when you treat this with methyl iodide, you should know one logic, that this is a halogen which is delta minus, your carbon is delta plus, and we know that alkyl halide likes to undergo nucleophilic attack. So your Na and iodine will get lost as NaI, and the product obtained in that case would be one carbon atom would be added. So over here, instead of 5 carbon atom, now you will have got 6 carbon atom. That means you have got now your product as hex 2-ine. Now only the last step is left out, how to convert this hex 2-ine to cis. And I think so only the last part is left out, where you need to convert your hex 2-ine to cis. Now basically alkynes to be converted to cis can be done by Lindlar's catalyst, and I think so. What is Lindlar's catalyst, child? We have got H2, along with that Lindlar's catalyst to be used. Now what is Lindlar's condition? Yeah, Lindlar's catalyst, child, it's nothing but you have got a palladium used, and along with that you have got carbon, or you have got barium sulfate, and in doing this, child, what will happen? Your hex 2-ine will get converted to cis hex 2-ene. So I think so the correct option for this MCQ has to be option A. I hope this is clear, child. Let's proceed with the next question, child, what we have on the screen. Now I think so the question what you can see on the screen is nothing but, consider the following reaction what you have got. Yeah, and what has been given over there? You had got one alkene given to you, and what is that alkene? It's something like this, child, mentioned with a double bond having a quaternary carbon atom, correct? Now it has been treated with Hi. Now basically what is this reaction? I think so it's nothing but an addition of Hi across a double bond. So let's use a mechanism over here. The first step would be a protonation. Now when a protonation takes place, the first step has to be a formation of more stable carbocation. So what will happen? The product obtained in that case would be something like this, where you have got a carbon skeleton, here you have got a branch, and your proton has been attached over here, so you will get a positive charge over here. Can I call it a secondary carbocation? Correct? Now there is a scope that the secondary carbocation can get converted to a more stable carbocation also by a rearrangement, and that's called as a methyl shift what you can have over here. Now what is basically in this case a methyl shift? You can see one of the methyl group will get shifted, so your quaternary carbon will get converted to a tertiary. And what will happen? Just see over here you have got this type of a molecule, child, where your methyl is shifted over here, so your positive charge will come over here. So your secondary carbocation is got converted to more stable tertiary carbocation. Now what? Obviously last step has to be a nucleophilic attack. Now when a nucleophile which is I minus will attack yes to the first component, first cation, the probability product what you can have was this type, where you have got a branch and iodine will also would be there. Now, if suppose if this ion is also formed, suppose means basically you have got this ion in a major amount. So, here again what will happen, your I minus what is a nucleophile will attack at this position, you will get the answer as something like this child, where even iodine would be there. So, I will write it once again child properly. Over here you have got one branch, over here one branch, and you have got iodine over here. So, there are two products which I have got. Now, out of these two products, one has to be P and one has to be Q. I don't know which one is P and which one is Q child. Let's now see what are the other information given to us. Now, see, compound P, yes, out of 2 when treated with alcoholic KOH. Now, see, if you see KOH is given an alcohol. So, it is an alcoholic KOH which indicates elimination reaction. Now, in elimination child, let us do elimination. Suppose if this is the compound which I carry out elimination by using alcoholic KOH, what will happen? Now, we know that leaving group attached carbon is called as alpha, and from the next carbon atom you will have a loss of H because we do not have other side. So, the product obtained in this case would be of this type child, where this will be nothing but your alkene, yes, which is nothing but your A product only same. Now, let us try same elimination reaction over here also. Now, when I use again alcoholic KOH over here, what is the story? This is nothing but your leaving group, and from this position you will have a loss of your H. That means the product obtained in this case would be alkene, yes, correct. Now, the question is, let us see properly what is the question. So, when this reaction takes place, you get a product P and Q, correct. Now, which one is P and which one is Q? I do not know out of these two. This is one of the case and this is another case, but out of this which one is P and which one is Q, we do not know. But now, what is the other information given to us? P on treatment with this gives you A. Now, P on treatment with gives us A. Acha, and one more information is given, tetra substituted alkene isomer of A, means out of this, if you see, this is an alkene but it is a mono substituted, this is alkene which is a tetra substituted alkene. That means if they are talking about tetra substituted alkene, then your correct option has to be this one, which is nothing but my P, and this is nothing but my Q product. Now, they have asked what is P. So, as you try IUPAC, this would be carbon number 1, this would be carbon number 2, this would be carbon number 3, this would be carbon number 4. So, it is a butane containing 2 methyl groups and 1 iodine. Iodine position is second. So, I think so it is a 2 iodo 2,3 dimethyl butane. So, your correct answer for this MCQ is B. I hope this is clear child. Let us proceed with the next question. Now, child, over here I think so we have got 3 reactions, yes, reaction 1, 2 and 3. Everywhere if you see, it is nothing but a nucleophilic substitution reaction, and that is also through SN1 mechanism, because everywhere we have got carbocation formed. So, now let us write one discussion what we have done. Reactivity order of substrate is always directly proportional to stability of carbocation. Now, just see which all carbocation we have got. In the first reaction number 1, we have got a tertiary carbocation. In reaction number 2, we have got a secondary carbocation. In reaction number 3, we have got again a tertiary carbocation. So, out of this 3, which is the least stable carbocation? I think so secondary carbocation is the least stable. Yes, correct. Now, out of the reaction number 1 and 2, that means your reaction number 2 will be less reactive, reaction number 2 will be less reactive, reaction number 2 will be less reactive. So, here as per see the situation, this cannot be the answer, even this cannot be the answer. Now, only the deciding factor is 1 and 3. Now, over here if you see, the leaving group is bromine and in this case the leaving group is Cl. Now, if you know one of the parameter to decide the nucleophilic substitution is leaving group ability, and good leaving groups gives better reaction, and I think so out of chlorides and bromides are better leaving group. So, in this case your reaction number 1 would be faster as compared to reaction number 3. Reaction number 3 will be more better than reaction number 2. So, your correct answer in this case has to be option C and not B. I hope this is clear, child. Fine. Let us proceed further with the next question. Now, here child, given reaction is there, I think so you can see very clearly. I will just do one thing, I will just make some adjustments over here, and let us write the reaction. Over here, basically, what is the step given to us? They have given one compound, and that compound is something shown like this, where you can see it is a 4-membered ring having a carbon atom, having a Br, having 2 methyl groups, which you can see very clearly. Now, what is they have given? The first step, heating is also given, methyl alcohol is given, X is a major product among the elimination product, that means it is very clear it is elimination, and in elimination it is an even mechanism. Now, basically what is the first step in elimination reaction? Leaving group will go out, and once the leaving group is gone out, will I get nothing but a carbocation formed? Yes. So, let us write the carbocation. So, here I have got a carbon having maybe one CH3 over here, maybe another CH3 over here. So, now what will happen? Here you have got positive charge. Now, what you will do? Yes, there is a scope for a rearrangement, and here we can try for ring expansion. Now, what is ring expansion? Over here, let us see how to do it. Over here, I have got a 4-membered ring, you can see very clearly. This compound can also be written in one more way so that you understand it little better, and I will put it in that way. See, this can be written as it is a 4-membered ring having one carbon atom which has got 2 methyl groups. So, I think so this is one and the same thing, only just represented in a little different manner, that is all. What will happen now? Ring expansion can take place very well. So, the structure what you are going to get would be of this type, where you have got over here a carbon having 2 methyl groups, correct, and now this bond instead of joining over here should be joined over here, and hence you will get a positive charge over here. Can I write this structure in one more way, in a better way? Here I have got total 5 atoms, you can see very clearly. So, here this is a 5 carbon atom situation, correct. Now, if I have got this carbon atom having a positive charge, suppose let us say I have got 2 methyl groups over here. Now, since rearrangement is already done, there is one more scope to have one more time rearrangement. Why? Because here now you can have again a methyl shift again. So, what is going to be the situation? It is like this, a 5-membered ring having one methyl over here, having another methyl over here with a plus charge over here. Now, last step I think so has to be what? Deprotonation. And what will happen? You will get nothing but H lost from here, and that is why your alkene has to be a 5-membered ring having 2 methyl groups, which you can see clearly, and having a double bond in between that only. So, the most common option as per the answer, yes, obvious option is answer C. I hope this is clear, child, correct. Let us proceed to the next question, bacha. Identify the product in the following reaction. Now, before we start anything, child, can you see over here the reactant and the product? It is basically telling that it is a substitution reaction. Now, in a substitution reaction, it is a nucleophilic substitution reaction, point number 1. Point number 2, I think so this is aryl halide and this is alkyl halide. Aryl halide will not undergo substitution reaction, that is very clear because of resonance stabilization. That means your fluorine should not change. Now, if you see over here they have done substitution over here, which is not possible, that means this cannot be the answer. Even this is not the answer, which is not possible. I hope this is clear. Now, if you see the next step is given is DMSO. I think so you must be aware that DMSO is nothing but a protic polar solvent, and even a nucleophile is also nothing but a negatively charged. So, here the tentativeness is about SN2, and in case of SN2 you I think so get child what? Final product is 100% inversion in configuration. Now child, if you remember, this bromine is given dark, means it is coming towards the observer outside the plane. So, your attacking nucleophile will come and attack from the back side. That means the arrangement or the orientation of SCH3 and Br should not be same, it has to be opposite, and hence you see here Br is dark. So, the attacking nucleophile has to be away from the observer, that is inside the plane, what we call it as a dash wedge. So, this cannot be the answer. Even this, what you can see, is the most probable answer as per the answer key. I hope this is clear, child. Let us take the next question what we have. Question number 13. Now see, here one compound is given cyclopentene, and here you have got a diol formed. Here also there is a situation diol, here also diol, but now there is a difference. Here both the OH groups are on the same side, so we call it as syn-diol, and here both the are opposite, we call it as anti-diol or trans-diol. Is it term clear? Now I think so this is one of the very common concept that when an alkene is been undergoing an addition reaction under some reagents, we have got syn addition and anti addition. So, remember one thing child, alkaline KMnO4 cold alkaline KMnO4, which we know it as a Bayer's reagent, Bayer's reagent is known for syn mechanism or syn addition, whereas so it will going to give you nothing but syn-diol as a product. Whereas suppose if per acids are used followed by hydrolysis, it will have mechanism which is called as anti mechanism, or you can call it as anti addition. That means in this case the product would be anti-diols. So, the answer is, I hope very clearly, reagent 1 has to be alkaline KMnO4 or something like that, and the reagent 2 has to be per acids. Now, the most appropriate option out of 4, what you can see is nothing but your option, I think so, is B, because your reagent 1 has to be cold alkaline KMnO4 for syn-diol addition, and reagent 2 has to be per acid, I think so it's a peroxyformic acid. So, I hope this answer is clear. Yes, let us proceed with the next question. Now, you have got the next question child on the screen is, they have given one epoxide shown over here. Now, let us write that epoxide child. The structure wise we have got over here a cyclobutane ring having one methyl group, having one oxygen, over here oxygen. Now, the question is child, before we start, the reaction is with HBr. Now, before we start anything, do we know that HBr is an acid which will have H delta plus part and this is delta minus. The first step will be a protonation. So, the answer what you will get is nothing but 4 membered ring having oxygen, having H over here, positive charge with a methyl group. Now, since we know that in this case what is going to happen, acid catalyzed reaction, so generally a carbocation tendency formation is easy. So, which carbocation out of these two will be more stable? If you break from here, you will get nothing but the answer as OH, you have got CH3 and this will be plus. So, here you get a tertiary carbocation. I hope this is clear child. Fine, sure. And suppose if I break the other option like this child, the answer would be of this type, where you would have got over here a CH3 and OH on this side, and you would have got a carbocation. Now this would have been a secondary carbocation. This is nothing but tertiary. Which is more stable, child? Yes, this one is less stable. This one is more stable. So the correct one what we have is this one only. Now last step. I think so you have got Br minus in the as a remaining part of a nucleophile. It will attack over here. So your answer has to be a 4-membered ring having 1 methyl, 1 Br and 1 OH. I hope this answer is clear. So the correct option for this MCQ what we have got is answer C. Yeah. Can we proceed with the next part, child? Let's go ahead. Now this is one of the very common reactions, child. They have given phenol, and phenol has been treated with carbon dioxide plus NaOH. I think so this is one of the very common reaction. I think so we call it as an Kolbe's reaction. Now what is Kolbe's reaction? Let's see, child, what we have. So we are just, I'll make it a small little bit. Yeah. Now now I have taken over here a phenol unit. Now when a phenol is treated with carbon monoxide and NaOH, I think so the product obtained would be a salicylic acid. A product obtained would be a salicylic acid where there will be an OH part and there will be a carboxylic acid part. Is it done? Now this is nothing but a first product. Now what is the second? Let's see on the arrow what we have. I think so on the arrow we have got PH, OH, and along with that we have got H2SO4. Now before we start anything, just tell me one thing. Phenol basically can be told as like an part of an alcohol, not as an alcohol, but yes, it's a phenol. It's a phenol, of course. So I'll put it over here, phenol only as a proper term. Now, who will react with a phenol? Acid part or a phenolic part or the phenolic part? The answer is acid will react with that phenol part. So what will happen over here? Your OH part of this and H part of this will get lost, and you will get the answer as benzene. Your OH part will remain as it is, and your CO part will be this, and that will be replaced by an pH. So have you got an ester formed in this case? Now what is the final reaction? Even the final reaction is given as, they have given us as pH COCl as the compound, along with that pyridine. Now we know that this is nothing but known as acid derivatives. It is an acid derivative. So basically it will react with OH containing compounds like alcohols or phenol. So over here you can see you have got a phenolic part H, and from your Cl, which is a leaving group, will go out as HCl, and the product in this case what you will get is nothing but a benzene ring having CO with OPH, and here also there is a new group O with COPH. I hope this is clear, child. So the correct option for us in that case is, both the groups have been there in this case. Is it clear? So the correct answer is C. I hope this is clear, child. Let's proceed with the next question. Now I think so here we have got one question where there are two functional groups, one is ketone and one is anhydride, ester. So they are given Grignard. Now Grignard can react with both the groups, but the problem is what? They have just mentioned 1 mole. So the answer is what? Will your ester will react or will your aldehyde and ketone will react? Now child, you should know one thing, that your Grignard reagent, yes, undergoes over here nucleophilic addition reaction. Now the question is, out of ester and ketone, who is more easy to undergo addition? And I think so, yes, the answer is ketone. Answer is ketone and not the ester. So your Grignard will try to attack always a ketone. So this is delta minus part. Yes, this will go and attack over here, and you will get nothing but the answer as tertiary alcohol. So your product should have a 4-membered ring. Over here you should have your ester as it is, but here you should have a tertiary alcohol. Yes, so let's see what is the option. Now here what they have done, if you see, they have kept a ketone as it is only, so this cannot be the answer. Here if you see, they have changed only the ester group to some other group, which is also not the answer. Yes, in this case child, if you see, here you can see clearly ester is given, yes, and your ketone has been converted to a tertiary alcohol. So the most appropriated answer what you can see in this case is answer C. I hope this is clear. Let's see the next question what we have on the screen. Now, the most probable product of the following reaction is. Now, let's first of all see what is this reaction. I think so we have got over here carbon total 5 with H over here, it's and you can say aldehyde group with a Cl over here. Now I have got a reagent called as methyl magnesium bromide. Now what happens? Let's see child. The first step, as usual we know that it's a delta minus part, it's a delta plus part. Obviously aldehyde and ketones like to undergo nucleophilic attack, so aldehyde will always react with Grignard to give you secondary alcohol. So let's write that it will attack over here, yes, and this Mg part will go over here. So the structure what you will get in this case would be a 5-membered ring. Sorry. First I'll put it as Cl over here. Here we have got an O with Mg Br, correct. I'll put this H inside only, no need to show, and here you will have got that group called as CH3. I hope this is clear. Now second step is hydrolysis. Now when the hydrolysis takes place, what will happen? This group will get hydrolyzed, so the compound obtained would be of this type, where you have got one methyl group which has been added due to Grignard. It has got one OH, and here you have got Cl. So this is nothing but my product, but since you know that you have got alkyl halide, this is nothing but your delta minus part, it's the electrophilic part. Here we have got a nucleophilic part. Can it attack over here? And once the attack takes place, let's see what do we get. Just check. I'll write this compound once again in this format, that you have got over here a Cl, correct. Now these two carbon atom I can make a shape over here as one carbon over here, second carbon over here, and on the third carbon atom we have got over here oxygen, correct, and to it you have got one second, and just will write once again. This is one carbon atom, this is second, and this is the third carbon atom. So here also we have got a third carbon atom, and then that third carbon atom is having OH part and one methyl part. So what will happen? Obviously this is going to attack over here, this particular part will get lost, and later on this H will go. So will I get nothing but over here what a structure would be? I think so, a 5-membered ring, yes, where one methyl group will be over here and one methyl group will be obviously over here. That means I'll get a cyclic compound, and I think so the most common option what you can see is option A. I hope this is clear child. Yeah, let's proceed with the next question, Bacha. Now here a hydrocarbon X on ozonolysis followed by treatment with dimethyl sulfide gives C7H12O2, and which gives positive Tollens test as well as positive iodoform test. The compound below satisfy the criteria of X is. Now before we start, in case of ozonolysis child, if you are aware, just simply what we do, I'll just tell you in short what we do. I think so, if you check, yes, during ozonolysis just we break the bond and put both the sides O. That means will I get over here also aldehyde, and will I get this side also aldehyde? That means it's a dial. In this case child, when you break it both the side, when you put O, it would be an aldehyde. it would be an aldehyde. In this case, if I break it, I'll put both the sides O. So, this side we have got aldehyde, this side we have got an ketone. Now, when you break on this side, child, you get aldehyde on this, oxygen this side, so you get a ketone and aldehyde over here. Now, basically just tell me one thing. The product what you have got will show positive tolerance test. That means it should have basically an aldehyde group. Yes. And positive iodoform test is shown by methyl ketone compounds. Methyl ketone groups should give this test positive. Now, here if you see, this cannot be the case, even this cannot be the answer. Only the two answers what are probable is what? Here you can have aldehyde to give tolerance test, but this ketone would be a pentane 3-one, and pentane 3-one cannot show iodoform test. Pentane 2-one can show, even this cannot be the answer. So, if you want to understand this, let us write. I have got over here the ozonolysis product where you have got aldehyde and here you have got and ketone. So, can I tell that this will show a test for aldehyde test positive and this will be a methyl ketone group which will give a test for iodoform test positive. Is it term clear? I hope the answer correct in this case is D. Let us proceed with the next part, child. Now, see the next question is what? A compound XC5H12O4 upon treatment with methyl magnesium gives 4 moles of methane. Identify the structure of X. Now, basically Grignard giving methane can be only one case, child. I do not know if you remember. Whenever Grignard reagent RMgX, yes, and instead of taking R, can I take it over here CH3 directly? Yes, because they have given methyl magnesium halide. When on treatment with protic polar solvent. Now, what are protic polar solvent? Water can be example of protic polar solvent. Even alcohols can be a protic polar solvent. Even ammonia can be an example of protic polar solvent. I think so you would be knowing this now. So, here you have what this is a delta plus part, delta minus part, delta plus part, delta plus part, delta minus, delta minus. Now, what? Since we know that Grignard part, what you have got is delta minus which act as a nucleophile. This is a positive part. So, what happens? The acidic part of these solvents, yes, will combine with this. So, everywhere in this case, will I get nothing but the answer as methane and the remaining byproduct. Now, important right now is not the byproduct, important is have you got a methane. Now, methane you will get only if you have got acidic H. Now, how many moles they have given? That means there has to be 4 acidic H. 4 acidic H has to be there. Now, how to find out 4? First of all, if you see over here, I have got only 3 acidic H. So, this cannot be the answer. I have got again a 3 over here, which again cannot be the answer. I have got over here a 3 acidic H, again this cannot be the answer. Yes, this can be answer because you have got 4 acidic H and all 4 Grignard will give you methane with this. I hope this is the correct answer and I think so you would be knowing also it's very clear. Yeah, I hope this is clear. Let's proceed with the next question. Now, they have given one question as an organic compound A C4H11N. C4H11N shows optical activity and gives N2 gas on treatment with nitrous acid. Now, before we start anything, if you talk about amines, we have got total 3 types of amines. One is a primary amine, another one is a secondary amine, and third one is a tertiary amine. Now, child, remember one thing. Primary amine when treated with nitrous acid, always it will give you alcohol plus N2 gas. That's very clear. and this is nothing but one of the laboratory or identification test for primary amine. So, they have given it gives N2 gas with nitrous acid, that means it has to be primary. So, your answer can be either this. Acha, this is I think so a tertiary amine, which cannot be the answer. This is a secondary amine, which cannot be the answer. Yes, even this can be the answer. I hope this is clear. But one more important part, if you see they have mentioned optically active. Now, this does not contain any chiral center, that means this is optically inactive. Only this is nothing but optically active. So, your correct answer in this case is D. I hope this question is not that difficult, but yes, is it clear, child? Let us proceed with the next part. Now, child, over here these are numerical based question, and we need to find out among the following the number of aromatic compound. Now, basically to find out aromatic compound, what are the parameters? I think so there are 4 parameters. The first parameter is the molecule has to be cyclic. Second parameter, the molecule has to be planar, where generally the carbon atom should have sp2 hybridized type of situation. Third, the third parameter is complete conjugation. I hope this is clear. And last is the one which is Huckel's rule. And what is Huckel's rule, bacha? I think so it's a 4n plus 2 pi electron. I hope this is clear. Now, based on that you can easily find out which are aromatic. Now, here, child, the first compound is one of the very common compound we have studied in past, it's cot, and this molecule, child, is non-aromatic, if you remember, we already done. Acha, this compound, if you see, contains a negative charge. So, here the total number of electrons are 4 pi electron system. So, this becomes again your anti-aromatic. Over here the number of electrons are 2 pi electron system. I think so this is aromatic in nature. Acha, this compound again, if you see, it's not an aromatic, it's a non-aromatic compound because it contains an sp3 carbon. Acha, this compound again contains a 6 pi electron, it's aromatic in nature, correct? Now, if you see that this compound, child, it has got 4 pi electron system, it's an anti-aromatic, child. I hope this is clear. In this case, whenever there is a minus, it contains one lone pair, so it's a 6 pi electron system, it's an aromatic. Acha, now in this example, child, second last, if you check, there are total I think so 1, 2, 3, 4, 5, 6, 7, 8, and even negative means this also gets involved in the resonance. So, here it's a 10 pi electron system, it is also aromatic in nature. Now, I think so this compound is also, I think so aromatic, it's a complete delocalization, and number of electrons in this case are 14 pi electron, which is again obeying Huckel rule, that means it's an aromatic. So, how many of them are aromatic in nature? Let us see, because they have told you to find out. First, I think so the aromatic one is this one, second one is this, third one already I have marked, fourth one I have marked, and this is the fifth one. That means the correct answer for this is 5. So, how many aromatic compounds are there? Total in all 5. Is it clear, child? Let us take the next question, bacha. Now, find out the number of stereogenic center present in the following compound. Yes, semivestilin. Now, this compound is something we need to just find out the chiral carbon atom, because it's related to that only. Stereogenic center means it's related to stereoisomers. So, now basically which all carbon atoms you can think? First, I think so this carbon atom can be one of them, which can be a chiral. Yes. Then you have got the next carbon atom, child, is this one, I think so. You can see this is also a chiral. If you check, this carbon atom is also chiral, because you have got one double bond, one H, one carbon, and this side also carbon having oxygen is the next. So, even this can be a chiral. Even this is one carbon atom which is not attached to oxygen, which there is a gap. So, even this is also chiral. Now, this carbon atom again, if you see, it's a chiral, because again the situation is separate. This carbon atom again, it's a chiral. That means how many carbon atoms, child? 6. Okay, one more carbon atom is left out, I think so, this one. Yeah, this is also chiral in nature. That means the total number of stereogenic center for this example is 7. I hope this is clear. Fine. Let's proceed with the next question, child. Now, the number of monobromo product formed by monobromination of ethyl cyclohexane excluding stereoisomer, child. Now, basically when you see the compound is of this type, having CH2, having CH3, correct? Now, this on monobromination, how many possible products can be there? Now, the first possibility is the product number 1, which is primary of this type. The second product can be this, which is secondary. The third product can be this one, which is tertiary. One more product what you can have is the secondary. One more product what you can have is again a secondary. And one more product you can have is nothing but a secondary. That means total in all you would have 6 products formed in this, excluding stereoisomer. So, I hope the number of product in this case is 6. Yeah. Let's proceed with the next question, child. Now, here, child, we have got 2 reactions, and you have to find out the major product, and then you have to find out the sum of the hyperconjugating protons in X and Y. Now, first what we can do is, let's write the first reaction, child. I have over here an OH, correct, and H plus ion. So, your first step has to be a protonation, child, if you remember. Yes. So, proton comes over here, there will be a loss of water molecule, I am writing directly. So, what will be the answer, child? You would have over here a compound having OH2 plus, correct? Now, what will happen? Water molecule is lost. So, I will remove it over here, I am just increasing one step. Yeah. So, what will happen in this case, child? You will have the structure something like this, where you will have a positive charge. Now, what else? Yes, you can carry out rearrangement. Now, here you can have hydride shift. Yes, so when you do hydride shift, the structure is going to be, because they have told you to give major product. So, here, yes, here you will have plus, correct, and when you do elimination, child, the product obtained in the elimination would be H would lost from this carbon atom. So, your product obtained would be of this type, having a double bond. Now, if you check in this example, this is my compound number X. I have got this as alpha, I have got this as alpha, and I have got this as alpha to show hyperconjugation. That means in compound X, I have got 8 alpha hydrogen. I hope this is clear. Now, let us take the next one. Now, the second one is this type of a molecule where I have a Br and I have got over here a bulky group. On the arrow, child, we have got TBOK. Now, child, if you remember, it's a bulky base. So, here elimination will take place, but as per Hoffman. So, here what will happen? This is alpha, and from this position your H will get lost because we don't have anything over here. So, over here your structure will remain as it is and you will get a double bond over here. I hope this is clear. Fine. So, now in this alkene, this is nothing but my product Y. So, as per the situation, in this case, the alpha H what you have got is only 1 alpha H. I hope this is clear. So, when you do a total, that is 8 alpha H from this and 1 alpha H from this, that makes total 9 alpha H's, because they have asked sum of the hyperconjugating proton. I hope this is clear, child. Let's take the next question. Now, child, what is given over here? How many amino acids are present in the following peptide chain? Child, if you remember, I had already told you something about this, that whenever two alpha amino acids are joined, we get one peptide bond. When 3 alpha amino acids are joined, we get 2 peptide bonds. If 4 alpha amino acids are joined, we get 3 peptide bonds. That means based on the number of peptide bonds, we can decide the number of alpha amino acids. Now, what is peptide bond basically? Whenever if you see this type of a group, I think so we call this is a peptide bond. So, peptide bond plus 1 will give me the number of alpha amino acids. So, you can see over here, can I have, this is one of the peptide. So, this is one of the alpha amino acid. Over here, this is a second peptide bond. So, this is a second alpha amino acid. Now, over here also there is a peptide bond. So, this becomes your third alpha amino acid and this becomes your fourth alpha amino acid. So, this is the first one, this is the second one, this is the third one and this is the fourth one. This is first, this is second, this is third and this is fourth. Basically, this compound contains 3 peptide bond and based on that also you can find out. So, the correct answer in this case has to be how much? How many amino acids? I think so there are total 4 amino acids as the answer key. I hope this is clear. So, kids, I think so in today's discussion we have done all these questions. Still, if you have got any doubt, you can come down to branch. Thank you very much.